welcome to the Innovate Europe podcast, where we talk to the founders and funders and all of those who make the European innovation ecosystems. I'm Clark Parsons, the managing director of the Innovate Europe Foundation. I'm also the CEO of the European Startup Network, and I'm really excited. I'm joined today by Alex Glätzle, the CEO and founder of planqc. A little bit of background on Alex. We're really excited to have Alex here, first of all, because the IE.F. Has just released a study on Europe's future in the quantum race, and there's nobody better person to talk to than Alex, an entrepreneur in this space. Really amazing history. Alex started out as a senior research associate in theoretical quantum physics at the University of Oxford, and then was a senior research fellow at the Center for Quantum Technologies in Singapore. So he's really been all around the world doing quantum work. Alex also worked as a consultant at Define before he then founded planqc, co-founded planqc, named, of course, for Max Planck. But for those of you keeping score and looking for it online, it's actually planqc, which is, I guess, a wonderful pun on quantum computing. So really great name. Alex has a really great study background as well. He has a Master of Science in Applied Economics and a Doctor of Philosophy in Theoretical Physics from the University of Innsbruck. Welcome to the podcast.
Thank you very much. It's a pleasure being here, Clark, and looking forward to the conversation.
Me too. We have just learned that the latest Nobel Prize in Physics has gone to 3 researchers in quantum. So before we jump in, what are your thoughts on these winners? Are they, I guess you would agree, they're worthy of the Nobel Prize?
Absolutely well deserved. We kind of expected that the Nobel Prize goes to the field of quantum computing, or basically the fundaments, because this year is UNESCO year of the World Year of Quantum Technologies. And in that case, it went to the fundamental principle behind superconducting qubits. So competing technology, but a very, very great approach, which is now pursued by Google, by IBM. And I was lucky that I met John Martinez, one of the Nobel Prize laureates, a few times in my life, on conferences and workshops. And he was actually also our mentor at the Creative Destruction Lab, which we won 2021-22 before actually founding and spinning out planqc.
That's amazing. I guess even though quantum is not the newest technology, and we'll of course get into it in the conversation later, but a lot of people in the field all kind of know each other, right? It's not that huge. You can still sort of know the legends and meet everyone.
Absolutely. For me, the time as a student, as a PhD student, this was one of the best times in my life, because I had really the chance to work in one of the world leading groups with Peter Zoller in Innsbruck, also one of the founding fathers of quantum computing. And we really traveled around the world from the US to Japan to Australia, and meeting all these geniuses, and suddenly talking to a Nobel Prize winner and realizing that the only thing which counts is physics and having smart ideas and brainstorming about ideas. This was super impressive to me. So the big learning was that there is no hierarchical feeling at all in those community. If you won a Nobel Prize or if you're a junior researcher, it doesn't matter. It's about the ideas, and that's a very open and encouraging community. And as you said, it's small. So we basically know the founders and a good part of the teams of all our competitors. And I think that's very healthy. On the other hand, I would be quite skeptic if there is a quantum computing startup appearing really from nowhere and you don't know any person personally behind that. That would make me skeptical.
That's interesting. I mean, this is really fascinating too, because you first studied economics. So what was it that attracted you into physics and quantum specifically? Because you had first started out doing something that wasn't physics or quantum.
Yeah, but that's not entirely true.
Mm-hmm.
I finished economic studies probably before my PhD, but I started it later, and the fascination was always about physics or about complex systems. And the world itself, economics, is also about simplifying really complex systems of individuals, companies, states. And so there are a lot of analogies, and I realized that in particular with some strong mathematical skills, you can really also do serious work, analytic work in the economics world, and that's what I enjoyed. But my passion for physics actually goes back to high school times. I remember once at Christmas time, I got this book from Stephen Hawking, Short History of Time. I was, I think, 12, 13 years old. And the entire holiday break, I was reading that book. And coming back to high school, I realized that not many physics teacher or people out there really understand that. So when I confronted them, hey, I read about entanglement, I read about spooky action at the distance, they were looking at me, hey, what are you talking about? Become serious again. And that even more encouraged me. Hey, there is a world out there which is so fascinating and so few people really grasp the idea behind it. And then I was really lucky that I got a very, very good physics teacher. And that's a story many of us unite. So it's of such crucial importance to have good teachers in that age. And he spent afternoons with us doing physics experiments and spending extra time in the lab because he loved it and he gave this motivation to us. And that encouraged me and actually several friends of my class to study physics then. And the next really lucky point in my history was that Innsbruck turned out to be really a world-leading center in quantum physics. It's one of the pioneers here. And there was really a critical mass, also an institute of the Academy of Sciences was founded in Innsbruck, a critical mass of excellent people, and that motivated even more to stay in that field.
Wow, that's was the field. There's kind of been a joke often about fusion and to some degree maybe quantum. You know, there was always a joke that it's 30 years away because this is the technology, or rather some of the principles are, you know, aren't brand new, but have taken a long time to develop. And now we're kind of in this race, as our study points out. Suddenly things are really speeding up. But when you got into it, it wasn't sleepy, but did you have could you feel that things were going to be speeding up in terms of the development and the actual utilization and going from theory to practice?
Definitely. So every time has its focus. And I think when I started my PhD or my studies, it was more quantum simulation. So the focus was not really on universal quantum. It was on simulating specific systems and building those systems with, for example, artificial devices, like using atoms instead of electrons, using laser fields to create potentials instead of real materials. And so these were toy systems, and this was a big adventure because you can explore these systems on the theoretical side, you can simulate them on a classical computer, and you can guide and bring ideas to real experimentalists, which then try that out. And I think the joke you made is also true for quantum. I think it's not 30 years, it was always 10 years away for a fault-tolerant quantum computer. And if you look back in history, this entire field started around 1994 when famous Peter Shor came up with the idea that with a quantum algorithm, you can do the factorization problem exponentially faster. And that, if that would be true, actually, if such a device would exist, that would be a real threat to all our security because asymmetric encryption, RSA, is based on this factorization. And the naive security concepts we believe in just relies on the fact that the best classical computer cannot crack that in a useful amount of time. But with quantum computers, you suddenly could. The funny thing is at that time, I would say nobody had an idea how to build these devices.
Mhm.
And it was I think a talk from Arthur Eckert, one of our scientific advisors, which then inspired my PhD advisor, Peter Zoller, and Ignacio Sirac, who is now also an advisor to Planck, to come up with an idea how to build such quantum computers, in that case with single ions. So this kind of opened the field of ion-trapped quantum computing. They soon realized that, and this is true till today, every approach has pros and cons, and the race is still open. One of the hard things to realize in ions is to scale them up, but also to make them faster. So soon after, they came up with a new idea how to build a quantum computer. This was around 2000, where they used neutral atoms to build quantum computers and really excite those atoms to macroscopic Rydberg states, where the electron is spinning around in a very large orbit, creates a dipole moment, and with those dipole moments, you can mediate this interaction. And so this was in the year 2000. And yeah, it took now 25 years almost till first startups appeared and this technology is ready to commercialize. And there are a lot of factors which are relevant. One of the most important factors is the supply chain. So in order to build these machines on a reliable basis with a high quality, you need, in our case, for neutral atoms, you need excellent lasers. You need ultra high vacuum systems and you need very good optics. And there's always a development in phases, and quantum computers is now not a big market, or was not a big market. So there is not much motivation for these laser companies to really put millions of dollars in R&D. But we were lucky that, for example, atomic clocks appeared on the market and really were one of the products which can be commercialized quite early on. And nowadays, on most of the GPS satellites, you find atomic clocks, which is a fascinating proof of quantum physics itself. But for those atomic clocks, particular lasers were developed and even improved. And that was a big pro for our technology because we can rely on those laser developments. And so these 10 years can easily explained by you have to have the progress in the full supply chain, so that the weakest point in the supply chain will hinder you to build this fault-tolerant device. And then still, there is also fundamental research. So we should not believe that any of the companies out there, independent of the platform, has a well-defined and clear plan to tens of millions of qubits.
Mm-hmm.
There
Yeah.
is still challenge and probably also on the fundamental research to tackle that. We have a clear plan how to build quantum computers with a few thousand qubits. We have ideas how to build one with 100,000 or up to 1 million. But up there, it's still an open field, and it's engineering. Money is required, but I also believe fundamental research will play a significant role.
This is a really great background, and I would actually maybe go a little deeper just for the listeners because I'm talking to somebody who has a lot of degrees in quantum and is at the cutting edge, and some of our listeners might have already gotten their heads spinning. I think it's important maybe for everybody just to understand that quantum is such a new technology that there are right now, I guess you could say, a lot of different ways to get to Rome in terms of how you could build a quantum computer. Could you back us up a little? And I mean, I think a lot of people already understand the principle of the difference between, how a qubit is fundamentally a different way of physically computing than, say, our traditional computer, which is, the integrated circuit. It's either on or off. And so your computer is essentially a series of connections. They're either on or off. And upon that, you can build thousands, millions of, ways to compute. But, as we know, or as many know, I guess, in the quantum state, you can be sometimes neither on nor off, or somewhere in between on a really sliding scale, which gives just an exponential set of possibilities for how computing can work. But could you just maybe give, just a quick primer on how Planck is working? Because you've mentioned neutral atoms, which is your approach. Why is it right now that we have so many ways? I mean, this technology has been around for a long time. It's fascinating that we still really haven't settled it, I guess is maybe the way to put it. Like, there are a lot of different teams out there, a lot of different companies out there, a lot of different researchers out there using quantum computing principles, or rather quantum physics principles, to try and build a perfect computer, but with a lot of different approaches.
Yeah, I think that's a great opportunity, that there's not only one approach, but many. And if you go back 100 years, and actually I mentioned at the beginning, it's 100 years of quantum technologies by the UNESCO. Those giants, Heisenberg, Schrödinger, Bohr, Einstein, if you would ask them, what is a qubit? They would probably told you it's the spin of an electron or it's the polarization of a photon. So an electron can, like our planet Earth, spin clockwise or counterclockwise around its own axis. And that could be logical 0 or logical 1. So these objects are quantized and can be in those states. And if you do the quantum magic, they can be in both states at the same time. So it's like our planet Earth spinning clockwise and counterclockwise at the same time. And this gives this remarkable, huge exponential growth of possibilities, as you call it. Now, controlling single electrons within atoms or ions or single photons, this is definitely a challenge. I mean, these are tiny, tiny objects. You need sophisticated technologies, lasers to control them. And this took now, I would say, more than 100 years. In the past 20 years, there was a very nice and exciting shortcut, which are superconducting qubits. So people said, hey, it's so hard to control these real qubits, these microscopic objects. Let's try to build artificial ones, really macroscopic objects, semiconductors, layers, and create superconducting currents. Like if you cool them down to absolute 0, there is a current flowing either clockwise or counterclockwise, and we can call that approximately like a qubit. That's exactly the approach companies like Google, IBM, or also our European player IQM is pursuing. These are artificial qubits. You have to cool them down that they actually become a qubit, and you have to manufacture them. So you have to manufacture them, and in the manufacturing process, you have to make sure that all of them are equal, and that's a challenge. Now, our approach came later, but I think we are on the fast track, and it's using neutral atoms, so using real qubits, storing the information in an individual atom. So probably the smallest unit of where you can store information, and we can trap those atoms in perfect square arrays, distance between these atoms of a few hundred nanometers to a few micrometers, in laser light, manipulate them with, again, laser light. So you need a vacuum chamber, you need lasers, you need optics. And the remarkable thing is this works extremely well, extremely accurate. The gates are super fast because these are ultra fast laser pulses shining on these atoms, and you don't have to artificially cool them. So there is no cryostat around. You don't need any liquid helium to cool them. These atoms are basically stopped in motion by laser light and trapped in these laser fields. And if we would measure the temperature of those atoms, then they are 1,000,000 times colder than deep space, the coldest place in the universe. And still, we don't need any artificial cooling. Everything works at room temperature. And this, I think, together with the fact that all these atoms are equal, we don't have to manufacture them. Nature kind of created them for us. We don't have to cool them, makes this technology so excited. And it's the technology which has the fastest way to scale to hundreds and thousands of qubits.
That's really helpful. Thanks. It's fantastic. For those of us who don't have the degree in quantum, that's a really great primer to try and get an understanding. And let's take a step back also about your personal journey, because you're seeing all of these developments in the research world, in the lab, and at some point you obviously decided we need to take this and make it a company. Take us on that founder's journey. What made you decide to leave academia and say there's actually great opportunity here to take this technology and build something with it?
Yeah, absolutely. I mean, one really remarkable visit was a research stay for a few weeks at Stanford University, where I met so many exciting people and realized that discussions in the evening in the pub only circulate about spinning out a company, startup idea, brainstorming business ideas. And there were all these people with their fancy startup hoodies, and people were pointing at another table and saying, hey, they just made an exit for 1 billion to Apple or to another giant. And it was a completely different atmosphere that we had here in Central Europe, like 15 years ago. So I came back to Innsbruck still as a student, and I was super excited about commercializing something. Maybe this was naive at that time, but I participated in startup competitions, one at this Institute of Entrepreneurship, Cambridge and Tirol from Hermann Hauser. And I pitched there already an idea about building a quantum computer with neutral atoms. And I actually won that competition. And that's where I met two very important persons now along our journey. One was Hermann Hauser, of course, and the other one was Markus Wagner, who also joined as a founding investor later. A serial entrepreneur from actually Austria who sold his company very early and then went to Palo Alto, to the Bay Area, to participate in the startup ecosystem there very successfully. And then I went back to my colleagues at university and actually also now co-founder today, and they told me, come on, Alex, that's too early. We're not ready yet. We have to prove several things in the lab first. And in retrospect, probably this was true. But then I left physics. I joined, as you said, a management consultancy firm. But this dream was always in my back head. And I was super excited when a few years later, Johannes and Sebastian, who I knew from the time of my PhD, called me and said, you always asked us about spinning something out. Now, actually, we have to do it. And I said, well, what do you mean this? You have to do it. What's going on? Well, there is the Munich Quantum Valley Initiative. That's a huge government initiative from the state of Bavaria, which wants to put Bavaria really on the global spotlight building quantum computers. So they at that point announced to put 300 million into the quantum computing ecosystem, purely on the academic side. But there was the clear intention from politics that there should be startups emerging from these grants, from these funds. And that was the birth hour of Planck, of our company. And I think this was a ideal situation for founding a startup. And that actually also convinced me to quit my job in consulting and start that adventure. Because obviously you have this huge talent pool in Munich around the Max Planck Institute, the universities. You have world-leading scientists. The Physics Nobel Prize went to the Max Planck Institute of Quantum Optics now twice in the past few years. And you have the political will, and you have a Bavarian government and a German government who really say, we put a significant amount of money into the ecosystem, and we want to be world leader in quantum technologies. And the third point, the last point is that, of course, you also have the supply chain. In particular, in our case, the laser industry, the photonics industry, the optics industry is particularly strong in Germany, in Bavaria. So having them basically door by door, having with them strategic partnerships to develop these machines is of uttermost importance. And then you also have first movers in industry. From the QTAC consortium, the German industry, in particular in Bavaria. And that was really what I immediately realized, that is the best place and the best timing to spin out such a startup.
That's great. It's great to get the support from the government and officials, but it's also interesting that you have been able to convince investors, and I think you guys have raised a 50 million Series A, which was quite a major milestone. It is a market where, IBM, Google, and others, as you noted, are working on what you guys feel is sort of a technology that ultimately in the long run you think you guys are much superior to. But still, it's a market where others were active, as our study even shows. a lot of these early quantum computing technologies have received a lot of financing. So you had to pitch investors and say, hey, it's a crowded field. A lot of people have got a bunch of money to build what we think is the wrong machine. So back us. I mean, how was it? How hard was it to convince investors? No, we've got the better mousetrap here, as the Americans say. We have the better approach. It's going to win. Take a risk.
Well, I would not say there will be a winner takes it all market.
Mm-hmm.
So I think this is important also for investors to realize. I personally believe, and many experts share that we will identify in the next years applications which work better on specific platforms.
Mm-hmm.
And in the long run, of course, we're all building universal quantum computers. So in the long run, I think the platform with the best technology, but also with the best and the earliest customer traction will win. It's always the combination of both. So I think looking back, what convinced our investors to invest a 5.6 million seed round into Planck was basically the team and being backed by the Max Planck Institute of Quantum Optics and the Ludwig Maximilian University. So having a world-leading team, Sebastian stayed more than a decade in the US, worked at Harvard, and Chilla, Johannes at Berkeley. I stayed a few years at Oxford. We all have a science background with an entrepreneurial spirit, and we have a Max Planck Institute in the background, which gave us a very important, very nice IP transfer contract, which actually now serves as a blueprint for many other spin-outs. And that basically convinced the seed investors. Then what followed with these 5 millions, we built up, the company structures, hired people, started building up labs, so whatever you can do with 5 billion. In deep tech, that's still a quite limited amount. But then a significant milestone was a 30 million contract with the German Aerospace Center. So this was a European-wide competition to build a neutral atom quantum computer. And we participated in that call. In the end, I know that many of our competitors, even worldwide, founded offices in Germany to be eligible to participate because this was such a unique opportunity at that time. And in the end, we could win that. And that was a technological milestone because it proves that we built really here on world-leading technology. It was, of course, a commercial milestone. And that triggered a lot of inbound interest from future investors. So after the press release went out, we were approached by investors basically worldwide. What's going on here in Munich? Who is this young company, Planck? And we used that momentum then to raise that 50 million round you mentioned last summer. And that's, I would say, a very important ingredient. What you see here, you need states, government agencies acting as first customers. And this is also a major point in the study you presented. There is no real market for quantum computers yet. Industry is hesitant for good reasons to put 30 million, 50 million in these technologies. And it's the responsibility of the state to speed up that, to act as a first customer, to assist startups building and developing those machines. And in the case of Planck, that works very nice because this really initiated this ping pong between public funded states acting as a first customer, and then triggering private investments.
Super. Let's talk a little bit about the use cases for quantum, because I think people now have understood that we're talking about a fundamentally different type of technology. So this isn't just like an incremental improvement. People are used to their computer getting a little more memory each year or a little more efficiency with the battery. And so, we sort of move up along, Moore's law with chips, and have gotten used to this kind of incremental improvement. Quantum technology, I think the reason everyone is so excited about it is because it can just go exponential. Hermann Hauser, we actually had him on a podcast here a few weeks ago, and he was noting, with each qubit you add, you sort of double the capacity in terms of computing power. So it's almost unimaginable how powerful a quantum computer can be in terms of the types of things it can do. But give people an idea of some of the the use cases that we've already thought of for what we could be doing with quantum computing. One of the things we all hear is that it's so powerful, it's going to essentially break all the encryption we have on the internet now, because encryption is simply math problems, and quantum computers could essentially break all of our encryptions. What are some of the use cases that excite you the most, maybe that people haven't even thought about, for where quantum computing can take us?
Absolutely. I just want to underline what you said in the beginning. Quantum computing is not just a new way of do computing a factor 2, 5, or even 10 times faster. It really, for the first time, enables us to calculate things which were really unthinkable to calculate before. I give you a simple example. A single aspirin molecule consists of around 20 atoms. This aspirin molecule can be in 10 to the 48 vibrational or rotational states at the same time. And you all need that states if you want to calculate in an exact way how such a molecule interacts with another molecule, how it reacts in your body, how it creates the effect you want. And quantum computing, for the very first time, opens the way to understand molecular dynamics, to understand how an enzyme couples to a receptor, to develop drugs really from fundamental principles or new materials. And that, for me, is one of the biggest motivations, that you can open completely new worlds in drug discovery, in material science, in chemistry, in general. I think about the situation where in 30, 40 years, we live in a world where you have personalized medicine. So basically, based on your DNA, a quantum computer will give you the recipe for exactly the molecule which has exactly the right reaction in your body to heal your diseases on an individual basis. Still, this is a dream, and we have to work hard to realize that, but this is definitely one of my big dreams. Another application you mentioned is, of course, encryption. This is, as I mentioned in the beginning, probably the first application which people realized, which Peter Shor pointed out. And this will threaten our entire crypto systems, from secure communication to Bitcoin and other encryption schemes. But as you mentioned, there is probably a way around, and this is post-quantum encryption. This is purely classical. This is a software layer of encryption you can add. And so far, we believe, and NIST in US did a challenge on that, we believe that there are 3-4 algorithms which we know today which are safe against quantum attacks. But still, the threat is real already today, not in 10 years when those quantum computers exist, because many of those hackers, they harvest the data now, steal the data now, accept that, well, we cannot read it today, but in 10 years, probably a quantum computer will decrypt it. Now, imagine a situation where your emails or bank accounts of famous politicians or a CEO becomes public today with the information 10 years ago. 10 years it's not so much. So I feel this is actually an immediate threat, and all companies should be encouraged to put this post-quantum layer as soon as possible. And the third application scheme, which is often discussed, is optimization problems. So optimization problems are one of the most complex problems we have out there, exponentially growing combinations of possibilities. There is big hope that quantum computing can do something useful, but there is nothing mathematically proven. So I'm always a bit hesitant to put the full focus on that scheme. I know that there are startups out there who built their entire business model on those optimization problems. But realistically speaking, we don't know yet if quantum computers will have this huge impact we expect.
When you say optimization problems, do you mean like optimizing stuff we're doing right now with some AI? I mean, is it logistics? Is it point A to
Absolutely.
point B? Like things that we're optimizing right now with an AI algorithm? You mean quantum could essentially,
Yes,
doing a heartbeat.
logistics is a great example. If you think about the traveling salesman problem, like in which order should you drive to various cities, for example, this scales exponentially with the number of cities and is a so-called NP hard problem. And this is super hard to solve on classical computers. They did enormous progress in the last few years. There is hope that quantum computers can tackle those problems, but I would say, or at least up to my knowledge, there is no mathematical rigorous proof that they will have this speed up there, and probably not an exponential, as I'm quite sure.
When before we were born, when the computer, or when computing was being born, I think there's these famous quotes about some of the leaders in the field saying, I think the world market could afford maybe 3 computers or 5 computers. Like, computers were a thing as big as a room, and no one dreamt that a couple decades later we would have in the 70s the advent of the personal computer. I mean, that was already, for the generation in front, just ahead of us, kind of a crazy vision that everyone could have a personal computer. Here we are with quantum right now. It's giant machines taking millions of dollars and euros to develop. Are we being imaginative enough about quantum computing? Do you really think in our lifetime, we're going to be having personal quantum computing? We're going to have, quantum on the phone? You know what I mean? Where can this get so small and personal and portable in our lifetimes? And if so, that's a whole new world of products and services that nobody's even really dreaming of, right?
I mean, looking back in history, and you quoted these famous guys, would be naive if I say this will never happen. I personally don't see also the necessity that we have these devices, a quantum device in our laptop or in our phone, because where quantum computers will have an impact in the near future is in combination with supercomputing. So as I mentioned, they should tackle the world's hardest problems, which are currently being run on supercomputers. And that's where they have their natural place, also in the next 10, 20 years. What comes afterwards, never say no. I would even say, we talked about applications just a few minutes before. I would say the real killer applications for quantum computers, we don't even know yet. Because looking back in history, who would have thought that these monstrous lab-filling computers once will be used to record a podcast like we are doing right now?
Mm-hmm. Mm-hmm. Yeah, absolutely. No, that's a really great point. I guess it's obvious, but why for you is it important that Europe invest in quantum computing and be there at the forefront of this technology?
For one simple reason. Our future of this continent will depend on those technologies, the wealth, the prosperity, but also the security of this company will depend that we can build and use. It's always a combination, those machines and the potential behind those machines. And it's one of the few examples where Europe really has still a chance to lead that revolution. There is a report also from the World Economic Forum in combination with McKinsey, who pointed out what are actually the key technologies where Europe has the best chance to lead. And quantum computing is on number one. And the reasons are obvious. We mentioned that before. We have the talent, we have the leading universities, we have the supply chain. We have to commercialize it. And that's usually the challenge here in Europe. But with those technologies, we cannot afford in the future to be dependent on any single other company. The security and the prosperity and the wealth of this continent will depend on it. And I think politics has understood that. And we have to be able to build quantum computers made in Europe. And even more important, we have to use them and create value out of them. That's the combination we need.
Super. Yeah, that's really helpful. We've just released a study as the IE.F. About how Europe can build on this momentum. And so even there, we had some recommendations for policymakers. I mean, off the top of my head, the first one was that we feel we should concentrate the funding on European players that have the highest potential. So that means making fewer but bigger bets. We feel that there needs to be a dual funding boost. There needs to be an effort to act as an anchor customer. I mean, you noted that one of the reasons why Planck even really got where it is today is because of this prize of winning a contract for 30 million in computation. When you look at also one other thing I think we noted in our study is that we of course need to open up defense budgets for quantum computing. When you look at some of these measures that we've outlined, what do you think is the most important one or ones to bring Germany and Europe ahead in this quantum race?
I think it's very important that we don't copy the rest of the world, that we don't copy Silicon Valley, for example. Europe has to define its own way, a smarter way, and this can only depend on technology and a technological advantage. We will never cope with the US or Middle East or China in terms of capital. If Europe says we will put 20 billion into quantum computing, then the US will say we will put 200 billion. So this race, Europe will not win. There is also a huge gap in venture capital versus US. We all know that. But the true chance in Europe lies in a technological advantage. If we find a smarter way, a way which fits better to Europe to build quantum computer, then I think we will win this global race. And in my opinion, of course, I'm biased, but I'm happy to read that your study comes to a similar conclusion. This is neutral atoms. Why neutral atoms? We have a huge heritage of talent, scientific results of top institutes here in Europe. We have the supply chain. So if you want to build a quantum computer made in Europe with neutral atoms, you need lasers and photonics, optics, vacuum technologies. We can all source that from leading companies here in Europe. That's a huge competitive advantage. Now, two very important points. Neutral atoms are the technology which scales fastest in the entire quantum computing game. Colleagues from the Harvard University have realized 48 logical qubits last year. Institutes like the Max Planck Institute here in Munich or the Caltech in California realized neutral atoms array with more than 6,000 up to 10,000 of those qubits, really proven this enormous advantage in scalability. And the fourth point, this is capital intensity. Neutral atoms all achieved these world-leading results with a significant lower amount of capital invested than all other technologies. I think in your study, you came up with numbers around 3 to 5 billion, which were invested globally in, for example, superconducting qubits, of course, by giants like IBM and Google. And still, neutral atoms are, in many of those KPIs, really front runner with a few hundreds of millions of capital. So in my opinion, focusing on neutral atoms as one of the world-leading platforms here brings a lot of chances, a lot of potentials here for this continent.
Yeah, that's really compelling. You mentioned the funding structure difference. Let's dive a little deeper on that, because the way that Europe, China, and the US are funding quantum is different, just in terms of size and structural ways. How can we in Europe get more funding into quantum? What do we need to do? Because yes, it's great that you guys have been way more capital efficient. I think in our study, we have the wonderful metric of qubits per euro or dollar invested, which is, off the chart for the neutral atoms approach. So it really does look like, just in terms of, investing, that it's a much more viable case. But we still need to get much more capital into this ecosystem. How can we do that in Europe?
Absolutely. I think Europe, and I think Hermann Hauser mentioned that in your podcast, doesn't have a startup problem, it has a scale-up problem. So it's really about the ticket sizes, 50 million to a few 100 million and above, where I don't know a handful of funds or investors in Europe which are able to do that. So naturally, you have to source that money from the US, from Middle East, or from other regions. So there is urgent need in Europe that we have a growth fund like that, and I think there are several initiatives. Hermann Hauser is also involved, one on the EU level, that there will be funds able to invest 100 million and more into scale-up companies. Another approach is that, of course, we have to attract international money from the Gulf region, from the US, but we have to do it in a more clever way. I think the French government did a very nice move by attracting significant amount of money from the Gulf region, transferred it in French funds, and this money will be exclusively distributed into the French ecosystem. That could be an approach we do European-wide or in particular in Germany. Now, venture capital is not everything. I think it's the fastest way to scale companies, definitely. But public money acting as a first customer, this is of almost equal importance. And here also we see the differences, for example, in the US, where basically the focus is entirely on venture capital, and China, where this is much more state-owned and publicly funded. And Europe probably should do the way in the middle. So activating more venture capital, this is definitely necessary, but also adding up more money on the public side, acting as a first customer. This also kind of is a very healthy balance for us, because all these fundings usually come in waves. And if you have more sources and you can kind of compensate these waves, that creates much more stability than a single source.
Super. One final thought before we go to the lightning round. You started out as a researcher and then, of course, went into consulting, but I'm sure you have had a lot of learnings as a leader running a company. It's a different muscle than working in a lab and, trying to just have breakthroughs in truth. What are some of the things you've learned about leadership in the process now of running Planck? And maybe are there some things you wish you had known when you started about being a founder?
So, of course, this was a crazy ride. Within 3 years, we scaled to basically from 1 to 100 employees. So company culture and maintaining company culture, that's something I completely underestimated. And in the beginning, you all sit in one office. So you interact with people for several hours per day, and it's natural that the company culture is reflected from the founding team on other members. If you scale, it's really of crucial importance that this culture kind of becomes preserved also over more hierarchical levels. So this is something I underestimated, and we had a dip in our journey, and now I think I'm back to great company culture and fantastic team. Another thing, I generally think a good leader should expect the same from himself than what he expects from the team. So you have to, first of all, work harder, work smarter, and then this gets translated to the team. In my life, I always had leaders above me acting like that, and that was most inspirational. And I tried to do at least the same.
Terrific. This has really been a fun conversation. Whenever we talk, I learn an incredible amount. I feel like I'm getting a small master's degree in the state of quantum computing, but also the state of being a founder in Europe. We've loved to finish our podcast with what we call the lightning round, just a quick set of some fun short answers. But one thing we love to ask is, if you had to start over outside of technology, what sector do you think you'd be pursuing your career in?
Probably music.
Music. Play an instrument?
I play the guitar and piano, but my brother actually is a professional musician, so I usually don't call me musician.
That's great. What's something you love about Europe? Which is also an interesting question for someone who has been to Silicon Valley, worked in Singapore. Clearly, there's a reason you're here and not there.
The life quality, and the quality of things, the social insurance net. I think this is something we completely underestimate what we have here in Europe.
And also the Alpine air, I would say, since you're from Innsbruck. what's
Definitely, yes.
what's the best piece of advice you've ever received? I don't know if it was from an academic or a business person.
Follow your dreams. I think this is something our parents learned us. I mean, I became physicist and then entrepreneur. My brother became musician. They never forced us in one direction. They really listened and watched carefully where we have our talents and then supported us to the best of their knowledge. And follow your dreams. This is also something I would wish for my kids.
That's really great. I would love to end on a positive note, something we love to ask people in this podcast because, we're all about European tech sovereignty. What's something that makes you optimistic about the future of Europe?
But it's this enormous accelerated development we have here in Europe. It's the motivation I feel every day when I go to the company from our team, but also the support from politics that they understood that it's of crucial importance that we control, own, and are able to use quantum technologies in the future.
Super. Alex, this was really a fun conversation. Thank you so much. And yeah, thanks for everything you're doing to drive Europe forward. I'm really, really excited, I think, as we all are, to see where Planck goes. And yeah, maybe before our lifetimes are over, I'll have a little Planck personal quantum computer on my desk. Who knows?
Yeah, hopefully. Thanks for having me, Clark. It was a really nice conversation. I really enjoyed it. Thanks a lot.
Super. And people who are interested in you can, of course, find you guys online at it's Planck, planqc.com or DE?
EU, actually.
EU. There you go. Silly me for not even realizing that. That's great. Well, thanks a bunch, Alex Glätzle, and good luck to Planck.
Thank you very much. Thanks, Clark.